So, all right. So, hi everybody. Thanks for coming. So, here we're going to talk a little bit about voice AI. Uh, it's a crowded room, so we'll have to see how that the actual demo works. But most of my slide is about my understanding of what I have building voice agents for the past year. Hi, I'm Vagbhi Mudumbai. So I've been writing code since 2001, and I have worked across multiple, things like mobile apps, desktop apps, distributed systems, DevOps, and off late for the past year, I've been, deep into voice AI and trying to understand how that works and how to build voice AI agents that kind of sound natural like humans and are able to speak, and converse naturally. So with voice AI agents, it's not like other AI agents because you now have to have these kind of like trade-offs. You need the voice to sound good and kind of immediately respond. So you don't want that 2-second pause to say, oh, absolutely, and then go from there or things like that. So you want to be able to have that latency, but at the same time you want it to be capable. So, and these are like two opposing forces. Like if you have lower latency, then you necessarily need, faster models that can immediately respond and you are going towards intelligence. And you also have voice quality as well, right? I mean, you don't want the transport becomes important. You need to make sure that you're on SIP or WebRTC and things like that, and the right kind of codecs so that the voice sounds good, like to a person hearing. So those are the three forces that we have to deal with, and sometimes there are trade-offs that you have to do, and you have to, pick and choose the right trade-off for your use case. So this is how most people are building voice agents these days. Uh, Somebody speaks on the phone, right, and that comes in as audio. That comes as a waveform, and we are going to send this to a speech to text model, where we convert the speech into text, and then we then send it to a large language model, which basically only ever deals with text. So it gives it, it gets the information that it has the system information out of it, and then it generates a response, and then it goes to a text to speech module, and then you get the audio output of it. So like text to speech, you have several companies there. You have 11 Labs, which is the big one. There is DeepGram, Cartesia, all of them. And with LLMs, you have the standard, the usual suspects from GPT-5 Mini or Gemini 2.5 Flash or Gemini 3 Flash. That's the latest, and so on and so forth. So, but let's take a step back and understand what is audio, right? And how does this work? So when you are speaking, as you say, eat your raisins outdoors on the porch steps. So you have a waveform, right? So when you speak, I'm actually making, pressure waves in the air, and those pressure waves are basically counted as amplitudes, like how much I am changing and how often am I changing this, and it's not ever this. So that's the waveform that it gets. So it's literally vibrations in the air that is there. So typically a waveform is mapped out like this, and this is called, they call it the time domain, because over time you see like different variations in the air pressure, and essentially you are sampling at 16,000 hertz or 44,100. Like for this MacBook Pro, it has an array of 6 mics, and it does it at 44,100 hertz. But usual microphones do it at 16 kilohertz or 8 kilohertz for telephone audio signals and so on and so forth. So once that's there, if you take a small window of that, like instead of taking the whole sign, if you take like a 25 millisecond window and you apply a Fourier transform on it, and you say, oh, you identify every single frequency that is there. Like, because when I'm speaking, it is not just the same frequency, but I actually produce different frequencies from my voice. And there could be background noises. There's this air conditioner that's running, that's producing buzz. So you actually have sounds at various frequencies that are in there. So if you apply a Fourier transform to see how is the distribution looking like, it'll look a little bit like this. The human range for audio is from 20 hertz to 20 kilohertz. Anything below 20 hertz, we call it infrasonic, and anything above 20,000 hertz, we call it ultrasonic, right? Our human ear can only hear these two, of which sound is, kind of in the lower part of the spectrum. It's anything between like 500 hertz, like the 20 hertz to 500 hertz is basically what our human ears are quite sensitive to. We can go up to 1,000 hertz, but anything above 1,000 hertz kind of sounds the same to us. It's all screeching sounds, right? That's about it. So in order to kind of map this better, so there is this thing called the MEL scale, and this was created, quite a while back, I think 15, 20 years back, when they were looking at audio signals and say, okay, when we have to represent these frequencies, I think it will be better if we map those 20,000 hertz of frequency scale and then kind of give more importance to the lower frequencies, because that's what humans like us hear, and it kind of reflects the way we process sound in our brains. So that's the MEL scale. So they take the frequency domain, they apply the MEL scale, and they create the spectrogram. So the spectrogram, again, x-axis is time, the y-axis is the MEL frequency that has been adjusted for, so the whole 20,000 hertz comes there. And then you also take the amplitude and you also do a log scale of the amplitude, because the absolute loudest that anything can be is something like a jet engine, which is like super loud. You have to have hearing protection around it and all those kind of things. Otherwise you go in and you have something as soft as a whisper, right? So, or something that's even low. So that is in the audio scale of things. But what you generally do is that you take the absolute highest of where you want the loudness to be. So, and you set it as 0 decibels, the relative 0 decibels, and you then kind of say how your audio processing should be. So if anyone has done podcasting or audio engineering or things like that, or fiddled around with OBS on those settings, so you'll have to actually figure out, okay, what's your noise gate level is going to look like, what is the gain that you want to apply to it, and so on and so forth. The idea is to get to that nice minus 20 decibels to minus 40 decibels frequency for the frequency that you are interested in, right? So if you're doing audio and speech, so you want to get anything from 200 to 500 hertz within that minus 20 to minus 40 decibels. So if that is there, then it's actually loud, clear speech that humans can understand. So all this needs to be done before it's sent to the model, actually. So let's talk about the way we have figured out, okay, how do we represent audio? After we represent the audio, we now have to figure out, what does this audio mean, right? What do these words mean? What do these sounds mean? And so on and so forth. So this is, on the left-hand side, this is from the Whisper paper. And what they do is they take the log-MEL spectrogram as the input, and they only ever work with 30 seconds of audio at a time. So even if you have like an hour-long podcast, they don't care about it. You have to break it down to 30 seconds. So you take the 30 seconds podcast, and then they do windowing on each one of these things. So their window width is again like 25 milliseconds window width, and of which 10 milliseconds overlap. So you create these windows. They keep hopping on these different frequencies, and then they try to build a semantic understanding of audio. So what does it actually mean? What does a semantic understanding of audio means? It just means that they project it into a big embedding space. So most of us have heard of RAG, how they work. Like you take it and you stick it into a vector database and so on and so forth. The same way, this actually creates vectors for these small individual tokens of sound. And this is at a semantic level, as in at that point in time, at the end of the encoder block, it doesn't resemble anything like the sound wave. It doesn't resemble any of those kind of things, but it apparently has the characteristics it has of like its surrounding sounds. Like if there is some sound, it knows whether it's a part of like plane or plank or any of those kind of things by paying attention to it, but there is no meaning to it yet. But it has that unique space of where each one of these sounds are. And then they train it along with this decoder block, which is like a typical GPT kind of like decoder blocks that's there, like GPT-5 or Llama or any of those kind of decoder blocks, and they have it pay attention to the encoder blocks that are coming in. So here, if you see down below, so there is the start of the token here, or start of transcription. Then they have the language in which this audio is. It's suggested, but it's not really necessary. Then the kind of task that it needs to do, whether it's transcribe or translate for this particular model, which was Whisper. And then they basically start giving these tokens that are there, the timestamp tokens and so on and so forth. And one of the cool hacks that you could do is you could actually give like the previous, so I told you that you could give like 30-second segments. So you could also feed in like the previous 30-second segments to it and then pass in the encoder blocks after that so that it can regressively generate the next token. So some of these things is like, oh, when there was like ads in a particular podcast or things like that, when we used to process it, we used to say, oh, this is a podcast which has ads just as text. And for some reason, their sample training set had all this data, and then it would transcribe it in the right language, even if the ad was in English and the podcast was in French or like in another language and so on and so forth. So this kind of the decoder blocks kind of make up and understand what the encoder block semantic representation of audio is, and then it does this. And of late, this is the latest state of the art in audio speech recognition is conformer. So conformer stands for convolutional transformer. So they figured that, hey, if you have the same kind of like Mel spectrogram audio coming in, so here it's the spectral augmentation that's here. So here, instead of 25 milliseconds, they even make it smaller, that's 10 milliseconds. But what they do is they slowly get it up to 40 milliseconds by just applying like image kind of techniques. So if you look at the Mel spectrogram, it almost looks like an image here, right? So it's like you have the X values, the Y values, and the color values for intensity. So you can actually apply a lot of image techniques onto this spectrogram's technique. So and in fact, that's how Suno and all of those work. They are called latent diffusion. They essentially are doing audio latent diffusion. So they essentially treat it as a image generation problem. So as long as you can generate the spectrogram image right, you'd essentially get the kind of sound that you want. Right? So that's what they're doing. So here in Conformer, they basically take the same thing and they use image convolution techniques. So they not only convolve by time, but they also convolve by frequencies, actually. So it's both X and Y that they convolve over. And then it leads to better understanding and also smaller models. So parakeet model, which is I think 300 million parameters. It's a pretty small model now. That's by NVIDIA, and that's like the best in the speech recognition. And they usually try to optimize for word error rates in this to do this. And here they also do this technique where they predict the token and the duration at the same time. So when they do this, it's not just text tokens coming out. They do text tokens by time. So if I speak very slowly, so they just are going to generate more tokens with like very first and a lot of nulls in between, right? So to do that. So that way they know how long a particular token is going to take, right? So they predict both the token as well as the time at the same time, actually. So that's Conformer. Sorry, I kind of like went ahead. So they combine both, both this size of this. And Conformer is getting more and more popular. I think there are a lot more models which are, especially the fast speech recognition only capabilities are using Conformer quite a bit. Now, let's talk about how to generate audio. Am I going too fast? Anything so far? Okay. Stop me at any point in time if you need to take a different path. I'd be happy to. So, and now let's talk about the text-to-speech model. So we got from the Mel spectrogram to the text tokens. Now we go from the text tokens to an audio waveform, but usually you have to go through a Mel spectrogram to get there. So this is actually a pretty cool TTS, model called Style TTS2. And there are several implementations of this. I think there is Kokoro. I think there's also Pocket TTS, if I'm not mistaken. There are a few of these smaller TTS models, and these are very small. Like Kokoro, for example, is only 82 million parameters. That's there. So it's a tiny model that can actually run on CPUs. There's also Style TTS2 was the original paper, just like 300 million parameters. And the cool part about it is you can actually do voice cloning. So you can take a voice and then you can say, hey, I want to take this set of tokens and I want to make it sound like the speaker, right? So to do that. And the reason you want to do that is like, okay, maybe you are generating a video and then you misspoke a word or two in between and you want to like fix that one particular thing in there, right? You want to basically, instead of re-recording this whole thing, you can just ask it to generate based on your voice with a corrected text or so on and so forth. So it started off with that, but it's also very useful in voice agents, so to speak. And the way that works is that they actually turn the words that we say into phonemes. So if you had ever used Google Translate and you said hello, it would also, or like say translate it to a different language and things like that. It'd also say how to pronounce it, and it would essentially be shown as phonemes. Phonemes are like, they have this international phonetic alphabet, so it's like a standard that's there, which says, if you say hello and it says H, and then it'll have like a weird inverted E and a different kind of an L and so on and so forth in it to actually say how it is pronounced. So those are phonemes. So you go from graphemes, which is basically our lexical text that we write, into phonemes actually. So it's called the grapheme to phoneme process. And that is usually like a straightforward algorithm that's there. Like there's like a very popular open source package called eSpeakNG, that which almost everyone uses to turn graphemes to phonemes actually. And this has been around for like ever actually, right? So you do graphemes to phonemes, and then you get the text, and then you convert the acoustic symbols of that. You say, okay, this is how a phoneme should be. This is what you need to pay attention to when you have these phonemes. And this model is usually much smaller because you're dealing with only these individual alphabets, and you're not dealing with massive tokens. So usually like a vocabulary of a GPT-5 LLM would be 100,000 tokens, right? Or something crazy like that. But here, it would just be like 140 phonemes and symbols. So, and they are dealt with on a symbol to symbol basis. So you're, even though you're only giving like 20, 30 words or 100 words, since it's broken character by character, it needs to pay attention to a lot more. So your context kind of increases. Even though they are smaller models, you're paying the tax in terms of the amount of tokens that it needs to process, because it's processing character by character. So it gets that. It then constructs a hidden representation of the text in phonemes, and then it then figures out the style sample that is there, and then it says, okay, how long should it be spoken, what's the style in which should be spoken, and all that, and that basically comes in through that style samples that are there. And finally, there is a decoder which basically takes these two hidden representations and produces either a MEL spectrogram or a waveform. In most cases, it's going to produce a MEL spectrogram, and the MEL spectrogram will then be turned into a waveform by like a hi-fi GAN or something like that. And one of the cool things that I want to show here is WaveLM. Over the course, I think some of the best things that has happened in these LLM research and all that is like all these foundational models that are coming in, like BERT is for text, where you can actually generate classifiers on top of BERT because it has this general language, and they have trained it on a bajillion tokens. I think it's close to like 2 trillion tokens or something like that for modern BERT. Similarly, they did it for VIT, which is like the vision transformer, where they trained it on a whole bunch of images. And Google did this for WaveLM. So where they did this for like audio understanding, and WaveLM is like and they have speech, audio, all kinds of audio, like music, everything on it. So if you want to quickly say, oh, given this 30 seconds of sound, can you tell me if it's like rock or progressive rock or like alternative or whatever? Like WaveLM is kind of the model that you want to take up and then try to build smaller models on top, right? So WaveLM is great for this. So they have used WaveLM to now do like a GAN kind of approach to find out, hey, is the audio generated by this model fake or real, right? And they would give this, and that's how they trained the style TTS2 model. And this is like a pretty small and mighty kind of model that I really love, and I do this. The other approach to take, so this is all like semantic understanding, but you could also do the same kind of techniques for sort of like acoustic modeling, right? Now, instead of understanding what the text means, if you can say, hey, this is how the tokens that are going to get generated, then you can take the same spectrogram and convert it into these kind of tokens that are there, and those tokens can then be used to, kind of do the same thing that we do with text. So that means that you can use the same GPT architecture, or you can use the same sort of like a LLM decoding blocks to say, hey, these are text tokens. By the way, these are audio tokens. Just train them together. There's no difference in there. So if you can achieve that, that'll be great. And that's what encodec does. So encodec, what it does is that it takes these Bell spectrograms that are there, and what it does is that it converts audio into individual token blocks, right? Just like how you do for like a modern transformer to say, hey, this is token number 25 and 34 and 36 or whatever. So they have basically turned audio itself into these kind of tokenized languages. And the way they have done is pretty amazing. So again, as with anything, there is like an encoder, which basically takes the waveform. Here, they are not even doing it on the spectrogram. They are actually doing it on the raw waveform. So they basically get all the data into it and then give a convolutional process to do it. And then in the end, when it comes here, it's like a deep audio structure. So I think here, there's like 1024 tokens per this thing. So like the embedding dimensions for OpenAI is like 1536, but here it's like 1024 dimension length for each 10 millisecond of audio. And they take this and then they turn it into vector quantizers. So these are called residual vector quantizers. So they would basically turn this 1024 dimensional space and try to break it into like, chunks, like clusters of different spaces, and they would try to predict, okay, which one of these numbers are relevant for this? Like, should it go to this 1024 chunk or this one of this, or so on and so forth. So it kind of like breaks it apart into clusters of chunks, and that's how they turn it into tokens. And they have this concept called code books, where they say, so it's almost like a lookup table, and say, oh, this particular thing, if it gives this, then it means index number 25 of this code book, right? But then it will not perfectly match onto it. So instead of saying that this is this 1024 things, they say, oh, they have 7 more code books that are there, and say, you take the first one, whatever is the difference between that, you add the second code book to it, and the third and the fourth and the seventh. So by the time you get to 8 code books, you can roughly represent any kind of audio that's out there as tokens to this. I spent like 3 to 4 days just reading the paper, trying to annotate it, go back, and just trying to read the code base of encodec, because this is a very dense paper and a very, very dense implementation as well. So it was done by Meta, and they've done an awesome job of documenting this whole thing. And sometimes you're surprised by what comes out of these labs. And this is absolutely brilliant. And the training, here you see so many losses here. So you have the waveform loss, you have the this is like a typical GAN, so you have the discriminator and the generator loss here. Here you have the spectrogram loss, and then you have the actual waveform loss. So they have 7 different loss terms, and there's also here, there's another loss here. So they have all these loss terms that are there, and they train it simultaneously by predicting all these losses and minimizing all these losses. So that means that they have different quality checkpoints on the actual waveform, the Mel spectrogram representation of the waveform, the generator and the original discriminator waveform, and all those kind of things. And it's absolutely crazy to even see that this works, right? I mean, if you try to train 4 neural networks at the same time, or 7 neural networks at the same time, and all say, oh, you all need to, coordinate, this is like an amazing thing. And they had this, I think they had like 100,000 hours of audio trained at the initial one, and I'm pretty sure they've done a lot more, so they've done this. So now what it does is that now, since we can have these kind of tokens, so you can have these tokens, and then you have the audio, and then you can still do text-to-speech. That means that there is no separate speech to text this thing. You basically give the audio and text at the same time to these models, and they work. Gemini 3 Flash, Gemini 2.5 Flash, OpenAI has a special model for GPT audio, which actually does simultaneous audio and audio and text understanding, and they can all. These are like multimodal omni-channel models. So that's pretty amazing. And it still generates text, so that means that you still need to go through a text generation, text-to-speech kind of pipeline to actually, have it produce audio. But you saw that these are all tokens. So why can't we have both input tokens as audio and output tokens as audio, right? So that must be possible. And that is the latest and greatest. So that's done as well. So Gemini has this Gemini native audio model. OpenAI has OpenAI real-time models, and these are different models. And of course, there's the Gemini's native audio model is exposed via the Gemini Live API. OpenAI's real-time model is also has a real-time API behind it. Qwen 3 has their Omni models, and Qwen 3 has a Live API, and so they have all different APIs through which they are exposing their these kind of like omni-channel omni-modal models, right? Both image, text, audio input, and image, text, and audio output. So it's actually pretty insane. And I've been working with them for the past year, and I've actually seen them getting better almost every 3 months. I can actually see a pretty big quality bump in the outputs that they give. And the costs, unfortunately, are quite a bit higher than the typical text models, but the quality that you get out of this is absolutely amazing. So sometime, I think August last year, this is done by Sesame. So Qtai actually made the first implementation of it as a part of their Moshi paper, but then Sesame came and they kind of like did the standard like Silicon Valley marketing thing. They did it much better than what Qtai did it with Moshi. And so what they did was like they had 2-level decoders. So you could get audio and text tokens at the same time. That is, when you're speaking, you can give the audio tokens. And their first transformer will only generate the first token of the codebook. Remember, I told you that you could generate multiple codebooks here. So that means that for every audio token, you have to generate 8 more encoded tokens. Or if you're using this thing, there was also this 32 token. They were using the 32 token variant of it. So that means that every frame of audio that they had to produce had to have 32 tokens produced. And with audio, most of those tokens can be predicted quite easily by a smaller network than like a full language learning backbone. So here, this autoregressive backbone transformer that they had was like a 7 billion parameter model. And they also had this other smaller decoder. Given the first audio token, it would produce the rest of the 31 audio tokens, because they needed to produce 32 audio tokens per frame, and they had another decoder. So they had these 2 parallel decoders that were running to do this, and that gave them like a huge performance bump, almost like a 30% performance bump just by having these 2 things. So, and this actually improved their performance quite a bit on this thing. So, and for voice agents, like you have these 3 different pipelines that are there: the cascaded, half cascaded, and the fully native pipelines. But you also have other concerns that you always have to deal with. One is transport. So transport for voice is quite unlike what we have seen for typical web applications, because here we are dealing with SIP and RTP. They are both work on UDP, actually. They're not TCP, so that means that you don't have HTTP and connections and all those kind of things. They have very different ways to deal with this. And then you have WebRTC, which is improvement on SIP. So you still use WebSockets for signaling to say, okay, who's in the room, which other parties are there, and so on and so forth. But then the whole audio session description and so on and so forth basically is like on top of RTP or RTP secure. And they all have different codecs as well. So you also have to deal with LLM provider integrations. I told you that OpenAI has real-time API, which they have changed the API on me thrice now, past year. Gemini Live has been improving their APIs as well. They've gone from beta to V1. They changed a whole bunch of these things that are there. So you have to keep on top of this. In addition to that, you have to do transcriptions. So if you're doing the STT to LLM to TTS, your transcriptions are baked in because you're actually generating text and you're sending back text. But if you're doing audio understanding or if you're doing native audio, you also have to take care of transcriptions. And fun fact, when you turn on transcriptions in Gemini and you're speaking to it, sometimes what it says is not what you hear. Your transcriptions are completely off, actually. So what we do is that we take every turn, we record the audio, and then we send it back for transcription, and then we attach the transcription up there. And then you also have to deal with voice activity detection. So we have, and this is not provided by many of the models. So you have to make sure that when a user interrupts, right, you want the agent to stop, listen, and then talk back again properly. So that's called voice activity detection. So you need to basically make sure you're running these edge models directly to do that. And you also have to deal with noise suppression, the AC sound, the dryer running in the background, your traffic din, all that kind of stuff. And we have to do transcoding from in and out. Like voice, most of the providers are doing ULAW, 8K, whatever, as a part of SIP RTP. And then WebRTC is all Opus. But your backend providers may only speak PCM 16LE or something like that. So you have to make sure that you transcode in and out to the formats that the clients expect. Of course, you don't have to build everything yourself. There's an amazing ecosystem. So there is VAPI, which is like the biggest, it's very developer friendly kind of ecosystem there. There is also Pipecat. Pipecat is by Daily. So Daily has their cloud offering, and then Pipecat is their open source offering. And then you also have LiveKit, which does all the transport handling and so on and so forth. You can use LiveKit with VAPI and pretty much get this. And just a shameless plug, we are building Urai to basically solve this problem, where we have like a native audio pipeline with Gemini. We also have integration with OpenAI real-time as well. So we have a built-in JavaScript runtime as well for serverless tools, so that you don't have to stand up another server just to call a tool. You can write JavaScript scripts in there. We do transcriptions, recording, and then we have like a test environment where you can test your agents without actually having to make the phone call, right, to see what's there. And we integrate with Twilio and FreeSwitch as well. FreeSwitch is the open source software on which Twilio is built. So we already have a C++ module that directly goes into FreeSwitch to do that. And we work with since we have WebRTC compatible endpoints, you can basically use the JavaScript SDK, stick it in there, and then you can have embed voice agents directly within your app. So that's about us. With that said, let me try to do a demo. Let's see how that goes. Okay, so here, this is our app. So I have set up two agents here, like a inbound support agent. Our setup is very, very simple. So we have a prompt. We have a few tags that are there, like caller ID number, or what the current timestamp is, and so on and so forth. And then we have like a prompt that's there, that is in there, and then we can associate different tools with it. So for example, I have two tools, one for call handling and one for Twilio SMS. And these tools are very simple JavaScript. Like if you have done any OpenAI integration or GenAI integration, you'd immediately find this. So there is a tool annotation on top, and then there is like a method that you would have, and we basically extract all the JSTalk comments here on top and automatically generate a schema JSON. So you have these. So the send SMS is basically like a simple call to Twilio for sending the SMS. So this is just a standard fetch call that we do. So nothing special here to do this. So here we inject the secrets that you define here with meta.secrets.twilio account set and so on and so forth. This is like an environment like Cloudflare Workers sort of thing, right? So you just write your JavaScript and then we'll run the JavaScript for you. And we also generate the schema JSON based on this that is there. And once So these secrets are basically where these gets injected from the Twilio account said outgoing number and all these things. And you can come to agents and then you can talk to them. So fingers crossed, let's see if this works. I'm going to hit send. So here these the caller ID number, I'm kind of hard coding it just for our testing, but ideally when you're calling in, I mean, that number will automatically get injected based on the call number that you have. So I'm going to say speak and say connect.
Hello, I'm Urai Voice, your AI voice assistant from Urai Voice. We help developers build incredibly natural, real-time voice agents. And I'd love to tell you more or answer any questions you have.
Okay, go on.
Urai Voice is a platform for building
Yeah, you already
interruptible
told me that. How easy is it to build with Urai Voice?
It's quite straightforward. You can use built-in integrations or write JavaScript directly in the platform. We've seen people go from prototype to production in just days. Are you interested in a demo?
Yeah, sure.
Great, sending that to you now. I sent them the link to this number. Is there anything else technical I can answer for you? Yes or no?
No, that would be all. I think you're good.
Perfect. Thanks for calling and have a great day.
So it calls the hang up, but since it's on the yeah. Oh yeah, I have to disconnect the call. Yeah. So since we are on WebRTC, it didn't do anything with that, but usually it will hang up. And we also do some of these things where we actually inject reasoning into it. Where we do this. So whenever we do tool calls, we also inject a reasoning parameter into all these tool calls, and that actually helps with models, following the plan a little better. Right? I'll do this, and then we also show the traces in there as a part of the debug trace that's in here. Right? So the SMS, it will be very difficult. Yeah, but you can actually see the SMS. Yeah, here is the SMS that got sent. So, but yeah, SMS did come for real. So, all right. So that's what I had to show. And by the way, the signups are open. So you can actually go to uraiai.com. If you scan the QR code, there's a link there, and we're basically giving away $10 worth of free credits for people who sign up, and you can use that. So yeah, thanks for listening to me, and if you have any questions, I'd be happy to answer them. Oh, outbound? Okay. You can also, okay, outbound SDR. So she's the boss, by the way. So she's the CEO and co-founder. So let's do that. So actually, let's do. Okay, this is the inbound. So I'm going to do outbound SDR. So I can actually do this here, or let me try. Let's be a little brave. I'm just going to call and see if that works. Okay, so that comes. Let me answer that. Hello.
Hi, this is Urai AI calling from Urai Voice. I know I'm calling out of the blue, but can I have 30 seconds to tell you why I'm calling?
Yeah, go on. Go on.
I saw you're hiring for engineering roles. We help tech teams build voice agents in hours, not months. Are you exploring AI agents?
Yes, we are exploring AI agents.
Great. Many teams find 90% of their budget goes to infrastructure. Urai provides that out of the box. Would you be open to a quick demo sometime next week?
Sounds a little this thing. So, do you really think it can be done in weeks?
Yes, we provide the platform and tools to significantly speed that up. The demo can show you how. Are you available next week?
Yeah.
You're all set. You can pick a date and time from the calendar. Thank you for your time. Have a nice day. You're
It's
all set. You can pick.
And it sends like a calendar request for me. Yeah, I'll show the transcript as well. So you come here, and this is the outgoing call that it did, and so you can actually see the transcript and it sets so and it's quite natural, so you can interrupt it and let's. All right. Cool. Yeah. Yeah. Yes.
Thank you for the presentation.
Yeah. Yeah. Good. Yeah. Yeah. I mean, yeah. And if you can provide the feedback, I think that would be good. Yes.
Quick question. I
Yes.
used some of this, like lately.
It's really
The-
impressive.
Oh, thank
It's
you.
really impressive.
Thank you. Thank you.
The numbers, like the phone numbers, when I ask the model to say, okay, here's my phone number, and like it repeats the phone number, and it repeats it incorrectly, which
Okay.
is really weird. It seems that it gets exactly what it is as a text. But if I wanted to inject it in a tool, for instance, it does it correctly. But when I ask it to repeat, to know if it got it correctly, it repeats the bad number. That's really weird. I don't know if it's something that you have experienced yourself.
Any particular model that you
Gemini.
Gemini?
Yeah,
Okay.
native
So
audio.
the thing that I found with Gemini is that treat it as like a audio model and not give any intelligence to it. So even if you ask it for things, so what we do is we actually run a second loop behind the scenes and we keep sending it back text.
Okay.
So we run actually 3 loops. So one is the audio loop that happens, and then we run the transcription loop that keeps happening. We take the transcription and we send it as text, as a reference for it to do that, and that actually solves the problem.
Thank you.
And we ran into this problem earlier, so that's why we.
You guys workflow, because I'm working on a project where, for example, what we're doing, we're extracting elements from transcriptions, like entities, we're talking about people, trying to distinguish who's talking, because it's let's say we have 4 people talking together, trying to extract what they're talking about, who's talking, and when, what they're talking about. How would you do that?
So you have speaker diarization as part of multiple models. So it will not be in the live model, but as a part of like 11 Labs, or if you run your own sort of like a parakeet kind of model, you can actually do speaker diarization as a part of that, and you can actually extract multiple speakers and what they're speaking. And you can assign at least speaker IDs, and you get different speaker IDs, and you can correlate them with speakers.
Would you do it in the small 30 seconds chunks? Vectorize that as well?
Actually, it is
As
not.
metadata, or-
It's not really required. I think like if you use Gemini Flash or Gemini Flash 2.5.
No, we use small models.
Yeah, small models. Yeah, that would work. Yes. That still works with Parakeet. Parakeet actually can do speaker diarization with pi and note. So if you use Parakeet with pi and note, you can actually get speaker diarization. And diarization is actually a very small model.
Yeah.
So you can just tack on diarization along with this ASR, and it'll be perfectly fine.
Right, per topic.
Bird topic might work too. Yeah, but there's just so much to keep up with. It's yeah. Absolutely. Thank you.
Your native voice model into
Thank you for the great presentation. I've actually been implementing PipeCat myself on Colonial, and I just got it to work like a couple months ago.
Okay.
And I really find it interesting that you're offering the whole stack available. So essentially, my biggest issue was the response speed at this point. And I noticed your setup is very quick response, so that's great. I was wondering, do you guys do also French support in terms of in and out? How's that quality in terms of translation?
In fact, our customer here is
just gonna ask him if he had a
service provider, and they are trying to do their own French.
That's very interesting. I'll grab one. Thank you very much. I'm definitely interested in looking at possibly integrating this in my system instead of what I currently have. Because your solution pretty much fixes most of the issue I have today. So yeah, I'll definitely have a look at it more in details when I get home.
Absolutely.
Do you have a whole team working on this, or
You're looking at the whole
Yeah,
team.
or if you're looking for someone, I'd be happy to join your team at some point.
Absolutely.
But definitely a nice project, and yeah, when I saw PipeCat, I was thrilled because it is currently seems to be growing quite fast since January 2025, essentially. And yeah, so
One of the things is that
I haven't really played with that too much.
one of the reasons why we didn't use Podcast
just like
initially
the notion of like
was that
typing my
we
voice
wanted better
into, like,
performance, so we
OpenAI.
wrote it all in Rust, actually.
So I
the
haven't
entire
done
audio
that,
pipeline,
even though part of me would like
including
to,
the,
because I feel like it would be
voice
cool to
activity
just
detection
like
and all those kind of things
ask
is
questions
going
and have
to
like,
the
I
Rust
would
pipeline.
be down for
So
that, but.
it's significantly faster than what Python is able to give us.
Oh, so I guess.
And we also wanted to make sure that we
Interesting. I guess
kind of closely link
the
JavaScript
half
functions for
cascade
tool calling along with
Right.
this. So because we wanted to quickly to say, hey, just make this call. So
Yes.
it's like
That's what
it doesn't even cross over a process boundary.
Now it's
And when it's written down. So we were like, oh, this needs to be really good. And when we
Oh,
do
this, yeah. Like, he's bigger.
audio
It's
processing,
no, this is
noise
something-
This is
cancelling,
yeah, just like take photos of
quality and
babies.
so on and so forth. That is all done by the WebRTC audio processing, which is written in C++, and it has C header files, but you have to integrate it. There's no way we would have been able to do that in Python. I mean, I don't know enough Python C++
What day do you
internals for me to
think?
have like fixed it.
Right.
So that's when I thought, okay, just do it in Rust because it's.
So you
Are
built
you
the whole,
thinking,
the voice
Tuesdays
activity
or
detection,
Thursdays?
you built all that on your own?
For your double day.
We use open source models that are there, like Silver Lab is basically what we use for voice activity detection.
Because
WebRTC
have to
audio
pick up the kids
processing
on
is
Tuesdays.
a
Is
part
that the
of
children's schedule? Yeah.
Chrome stack, but you can essentially get
But I
a
know,
separate project to do
and
that.
it comes out
So
on
most of the core algorithms for this
Basically, we're
we
gonna come in
built.
and study on
I didn't build, it's just a one.
That's already my reality.
One dive.
I understand.
So,
No, you
but
know,
we
you
were
should
able
do-
to
you should
integrate
say
all
like
that as a part of
Wednesday
the
is,
Rust code.
Okay.
Because the goal
in
for us
office
was that, okay, we have like a 40-millisecond window for us
I see
per
some
frame
people do that.
to do this, per
Okay.
audio frame.
They
So
just
this.
block
So
off
that
the whole schedule to
when
say,
the overall
we have
latency that
meetings
we have,
now.
Don't book me.
doing this project
Don't book me a
is-
Zoom meeting.
So that's our latency budget.
Sure.
So.
A lot of my
40
meetings are
milliseconds
kinda ad
of
hoc,
audio
though, to be
processing,
honest.
calls, all of
Fair enough.
that.
We can talk. But yeah, I guess you
So, audio pipeline for transcoding, voice activity detection, and denoising is 40 milliseconds.
Which is quite fast.
Yeah, yeah.
And then do you guys, like right now, do you host your own, do you run your own models for the LLM part?
No, we don't. That's. I did explore that, but I found I'd be burning money if I do this now. Most of the hosted models are actually cheaper to run, and as long as we keep our infrastructure and architecture in a way where we can like lift and shift to a different LLM operator or things like that, it becomes easier. Although I feel like Gemini is like heads and shoulders above, like in terms of like maybe they have these weird intelligence issues, but they're fixing it because that is all a function of the data and not the model.
Right,
I think they're going to win big time because they have enough and more data to do that. So they just need to, allocate like training time for this, and then like once they do this, and then it would get better.
Yeah,
I think in a year's time, I think Gemini is going to be like clearly killing everyone else. So.
Definitely. Maybe you have questions. I
Yeah,
don't
sure,
want to take
sure,
up all the
sure.
time.
Yes.
I just said thanks for the talk. It was a great
Actually,
talk.
thank you.
I was just curious with like the native voice